about my work on variational inference in phylogenetics. Markov chain Monte Carlo is currently the most widely used method to do Bayesian inference in phylogenetics. Unfortunately, there's a scalability issue for big data sets. For example, for programs like Mr. Bayes and Beast, it's almost impossible to analyze 10,000 sequences and more. And from the figure, you can see now we've got almost 200,000 sequences of COVID-19. So you can imagine that the current programs cannot deal with this kind of data set. A little bit of a notation here. I'm going to denote my joint distribution as P, the latent variables Z, and observed variables X. X in our case could be a DNA alignment, and Z could be branch length. And we are going to infer Z through the posterior. Unfortunately, the denominator is intractable, so we need to approximate the posterior distribution. And usually we do this using MCMC. But like I said, MCMC can be slow for a big data set. So can we do better than that? I'm hoping that variational inference is the answer. Variational inference involves approximating a complex distribution with a simpler distribution. The recipe is quite simple. You just need to minimize the callback library divergence from the variational distribution Q to the posterior distribution P. From the formula, you can see it's quite simple. But unfortunately, we need to know the posterior distribution. Fortunately, there's a way to go around it. So if you just write down the callback library formula, we've got this, and we expand the last term, we get that, and we can notice that the marginal distribution is constant with respect to Q. So we can ignore P of X. And now instead of minimizing the KL divergence, we just need to maximize the evidence lower bound, which is called the ELBO. The ELBO is just the negative of the KL plus the log marginal likelihood. And the ELBO is called this way because it's the lower bound of the evidence. Now we know how to do variational inference. We just need to minimize. But now we also need to know what kind of variational distribution we can use. The most commonly used distribution is the mean field distribution. And in this case, it's a normal distribution, where each component is independent. So the latent variables Z are all independent, and they're all normally distributed. Another way to do it is to use a full rank Gaussian, where we've got a full multivariate normal distribution. Now I'm going to show you an example of variational distribution. Here on the top left corner, we've got in red the posterior distribution of interest. And in black, that's the variational distribution. Here in this case, it's just a log normal distribution. And we've got the parameters on the top left corner, mu and sigma. That's just some random parameters. And you can see that the distribution doesn't look like the posterior distribution in red. On the right, once I click start, you will see the ELBO. That's what we want to maximize. So it's going to go up. And here it starts from minus 1400. And then the bottom two panels, we've got the derivative of the ELBO with respect to mu. And the other one is the derivative of the ELBO with respect to sigma. So here we should expect that it's far from zero, and then it gets closer to zero as the ELBO increases. Here we go. So you can see using the algorithm that the black curve is getting closer and closer to the red curve. So the variational distribution looks like the posterior distribution of interest. And you can see the ELBO is going up, and the gradient is also near zero. Unfortunately, it's squashed because the starting values were very bad. And now we've discarded the 10,000 first iteration. So now we just focus on the last iterations. You can see the variational distribution looks like the red curve, The ELBO is still increasing. It's a bit noisy, but that's normal, and all the gradients are close to 0. So that's what it would look like when the variational inference work. So how did I do this? I use some kind of framework. It's called automatic differentiation variational inference. I use stochastic gradient ascent to optimize the ELBO. It's just a maximization algorithm. There's the word gradient, so that means we need to be able to calculate the gradient of the probability models. So that's important. In phylogenetics, for its fixed topology, it's easy to get the gradient, so that's not too bad. But you need to do it efficiently. And there's some library for this. Here I gave you 4. There's Stan. Stan is a nice programming language. There's TensorFlow, PyTorch, and Jukes. The last 3 are all written in Python, and that's quite easy to use. I've underlined Stan and PyTorch because I'm going to talk about them a little bit more later. Another big part of the recipe for doing variational inference is to be able to transform constrained variables. For example, branch length are positive, nucleotide frequency is sum to 1, and there's some node height constraint in a time tree. The age of the parent has to be older than the child node. So we have to take this into account. I was talking about Stan. Here is a simple script for doing phylogenetic inference using variational inference. This is just the Jukes Cantor model. It's unrooted, and everything fits in on this page for a fixed topology again. We've done a lot of work on using Stan, and we created a Python script called phylostan that creates Stan script. So you create the Stan script and gives it to Stan, and Stan is going to compile it, and then we can finally use it. And of course, it's based on a fixed topology. And here's a list of the different models that I've implemented in phylostan. You can do time trees, unrooted trees, molecular clocks, coalescent models. It's very easy to use. I've also implemented another program called physher. It's a C implementation, and it's just for variational inference in phylogenetics. Stan is for everything. It's for phylogenetics and any other model you can think of. And in this implementation, also I focus on a fixed topology. Like I said before, I need to be able to calculate the gradient. Stan, it was nice, he would just do it automatically for me. I would just write the expression of the likelihood, and from there it can just get you the gradient every time you need it. In physher, it's a different story. I have to do everything by hand. So I start on paper and then I have to write it. So it's a little bit harder than using Stan, and I've used this in a recent paper. I'm going to show you an example on a data set. It's a small data set. It's only 69 sequences. The model is quite simple too. It's just a strict clock. So we also estimate the divergence times. We've got an HKY model, a constant size coalescent prior on the tree topology, and also we have some rate heterogeneity across sites. And I tried both the mean field and the full rank normal distributions, and that's using phylostan. If we start on the left, that's just the mean field, where we ignore all the correlations between branch length. And here I just showed 9 parameters, 3 times 3. For example, the first one is the clock rate. The gray histogram, that's just the MC estimate. And the blue lines, it's 10 independent replicates of phylostan. So you see there's a little bit of variation, but they're all around the right answer, which we think is, here we consider the right answer to be beast. For the full rank normal, where we take into account the correlation between parameters, you can see that they're a little bit closer to each other, all the replicates, except for one. It's completely wrong. No, it's not completely wrong, but it's a little bit wrong. And I think that's a convergence issue. So it didn't run long enough, or the criterion to stop the run just was triggered too early. Another data set, this one is kind of famous. It's using an hepatitis C virus data set from Egypt. In this case, the substitution rate is fixed, but we still estimate the divergence times. The substitution model is just DTR. Now in this case, we've got a Skyride coalescent model and also some rated heterogeneity. And here again, I use phylostan and beast. So top left, we've got beast. Here we're just going to consider that's the right answer, and we want to be as close as possible to beast. So you can see that the variational inference, it's getting the right ideas, going up and down and up, but the confidence intervals are quite narrow, are very narrow. The reason for this, I think, is because it's not taking into account the correlation between parameters. And there's a lot of correlation between in the piecewise constant coalescence. The variational full rank is a little bit better. The confidence interval is a bit larger, but unfortunately now the age of the root is a bit wrong. So I think in this case, it was not run long enough. So how do they compare phylostan and physher? Language, phylostan is using Stan, a nice language. It's C++ under the hood, so it's not that slow. Physher is just written in C. The gradient calculation, that's very important in variational inference. In Stan, it's using automatic differentiation. So you just need to write once the tree likelihood, for example, and it's going to give you the gradient automatically. In physher, like I said, everything is painful. I have to write everything by hand. So it's nice to have automatic differentiation. Unfortunately, for speed, physher is much faster than Stan. But that's the cost of writing everything manually. In terms of flexibility, Stan is not very flexible because if you want to change something, you need to go in the C++ code, which is quite hard to do. In physher, there's no restriction. It's my code. I know what to do. I know where to change anything. So that's quite easy. And the tree space, that's a big problem for both of them. They just work on fixed topologies. So it would be nice to have the speed of physher, the gradient calculation of phylostan, the flexibility of physher. So what can we do about this? Really, we want something flexible and fast with automatic differentiation. That's a lot to ask. So one of the solutions where we opted for is to use a Python framework where we have automatic differentiation and give the slow calculation to another library, a specialized library for the tree especially for the tree likelihood. When I say we, I do this work with a lot of people. I will talk about them at the end on my last slide. So that's the solution, and that's what we do. That's what we're doing now. So the Python framework I'm using is PyTorch. Like I said, there's also TensorFlow. I know people that are using TensorFlow now for this. And for the library, we are creating a new library called libsbn. libsbn has Beagle, the Beagle library inside, which is a library used in a lot of things like Beast. So we use Beagle to do the calculation of the tree likelihood and also the gradient. And in this library, libsbn, there's a lot of other things. That's why I said extras. And there's a lot of things. So something about Bayesian subsplits, I think there will be a talk about it before or after me, I don't know. So it's doing a lot of things. And you've got the GitHub page at the bottom of the page. So is it good to use Python and then the library, an external library? The library is written in C++, so it's supposed to be efficient. So in this experiment, we are using different inference data sets. They're different because they have different size. So they range from 20 sequences to 750 sequences. The model is JC69, quite easy. We estimate the divergence times. We have a strict clock and a constant coalescent prior. And we've got 4 implementations now. So the 4 implementations we used 5,000 iterations. So on the x-axis, we've got the number of sequences, 50 to 750, 20 to 750. And on the y-axis, we've got the running time in seconds. So straight away, you can see that phylostan is the slowest one in blue. Then we've got the PyTorch implementation, what I call pure PyTorch. I'm not using libSBN in the pure PyTorch. It's all written PyTorch, so it's all Python. And you can see already it's much faster than phylostan. So which is a good start. But then when we use PyTorch with the libSBN library, you can see it's a lot faster again. And that's the red line. And importantly, it's getting very, very, very close to physher. Physher is the C implementation, everything coded by hand, the gradient analytically derived by hand. So you can see it's getting very, very close. So that's a very good sign. And in the case of PyTorch, we calculate the gradient of the coalescent model using Python, using autodiff. So I didn't have to worry about it. With libSBN, we just calculate the gradient of the tree likelihood. So it's very encouraging, this plot. But we still have some problems. One of the biggest problems in variational inference is how do we take into account correlation between parameters? There's different ways to do this. There's 3 ways I've listed here. There's probably a little bit more. Another problem with everything I've shown you, it's all about one topology at a time, and that's it. So in libSBN, it's going to include the SBN framework that Cheng and Eric Madsen have published about 2 years ago. So this is going to be included, and we're currently working on it in libSBN. And also a big thing, it sounds a bit silly, but we need to initialize the starting value a little bit better. Because when we start from the distribution in the wrong area of the space, it's very hard to get the right answer. And we can use some kind of Laplace approximation for that. I've done this work with a lot of people in the last 4 years, and they're all here. Eric is very motivated. He's going to give a talk, and his team. Michael is going to give a talk, I think, also. We all work together. It's a fun project. Thank you.